Hello everyone, I welcome you all to the course of heat transfer. In today's session, we will discuss some more problems pertaining to the topic radiation. The first problem goes like this. Two large parallel planes with emissivities of 0.3 and 0.5 are maintained at temperatures of 527 degrees Celsius and 127 degrees Celsius respectively. A radiation shield having emissivities of 0.5 on both sides is placed in between them. We need to calculate the first bit, the heat transfer rate between the two plates without the shield. In second bit, the heat transfer rate between the two parallel plates with the radiation shield. Now the given data is like this. You have two parallel planes. The emissivities of the parallel planes are 0.3 and 0.5. In first case, you need to calculate the heat transfer without the radiating shield. In second case, if we place a radiation shield in between these two parallel plates, then what will be the amount of heat transfer? Now, again, all the temperatures are in degrees Celsius. First, you need to convert them to absolute scale, that is in Kelvin. Now, the schematic diagram is like this. You have two parallel planes with a numbering 1 and 2. It is having an emissivity of 0.3 and this is having an emissivity of 0.5. It is at 527 degrees Celsius and this plane is at 127 degrees Celsius. In the first case, without considering the radiation shield, you need to calculate if these planes are at this temperature with this emissivity on each surface, what will be the heat transfer? In second case, if I place a radiation shield with the emissivity of 0.5 on both sides, yes, right? So at this phase also 0.05 as well as at this phase of the radiating shield is also at 0.05. Now in order to address the first question, that is heat transfer without the radiating shield, this type of problem we have seen in the last session, wherein two surfaces are at different temperature. Because of change in temperature, there will be heat transfer. Now that is given by Q12. It means heat transfer from surface 1 to surface 2. Sigma, you can consider area to be 1 if not given. So in this problem, he has not mentioned anything related to the area, hence you can consider it to be unity. into T1 to the power 4 minus T2 to the power 4 upon 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1, where epsilon 1 is the emissivity of the first surface, emissivity of the second surface. The value of sigma is 5.67 into 10 to the power minus 8. Now, if you substitute the value of T1 as 800 Kelvin and T2 as 400 Kelvin, and the values of emissivity as 0.3 for first surface and 0.5 for the second surface, you will have a value of 5024.5 watt per meter square. In this case, he has considered the area of radiating surface to be 1. Now coming to the second part of the question, that is, suppose if we place a radiating shield, then what will be the heat transfer? Now again, we need to consider the temperatures of the both surfaces. Now here, you need to consider the equivalent emissivity between these two surfaces and then the equivalent emissivity between these two surfaces. So from 1 to 3 plus 3 to 2 is the total heat transfer from 1 to 2. Now this radiating shield is generally introduced wherein your intention is to reduce the heat transfer. Now if you consider the same equation, you have heat transfer with shield as sigma T1 to the power 4 minus T2 to the power 4, and this equivalent emissivity is out of surface 1 and radiating shield, which is towards the left face, and this is the equivalent emissivity between the radiating shield and the surface 2. Now here, if you look at the problem, now on this side also the emissivity is 0.05, on this side also it is 0.05. Now first we will consider the rate of heat transfer between 1 and 3. Then we will consider the rate of heat transfer between 3 and 2. If you consider the equivalent emissivities, we will have a value of 859.45 watt per meter square. Now if you compare the net heat transfer without shield and with shield, you can see there is a drastic decrease in the heat transfer when we have used a radiating shield. And again, it depends upon the emissivity of the radiating surface. If the emissivity is more, we could have obtained a larger value. Moving to the next problem. Emissivities of two large parallel plates maintained at 800 degrees Celsius and 300 degrees Celsius are 0.3 and 0.5 respectively. Find the net radiant heat exchange per square meter of the plates. So in this case, he has given per square meter of the plates. It means you need to consider area to be 1 meter square. a polished aluminum shield with the emissivity 0.05 is placed between them, find the percentage of reduction in heat transfer. Now in this case, he has given temperatures in degrees Celsius. You need to convert them into Kelvin. He has given the emissivities epsilon 1 as 0.3 and epsilon 2 as 0.5. So I think he has made some mistake here. It should be 0.5 according to the given problem. Now he has placed a radiating shield, precisely an aluminum shield, which is having an emissivity of 0.05. If he has not given anything with respect to the other phases, so you can consider 0.05 is the emissivity on either side of the radiation shield. This is the schematic diagram. We have surface 1 here, surface 2 here. So this indicates an insulation. The heat is transferring from the inner side of this as well as from inner side of this surface. And in this case, you don't know the temperature of the radiating shield. When you are asked to calculate percentage reduction, you also need to know the temperature of radiating shield. As usual, heat transfer without the radiation shield will be sigma A into T1 to the power 4 minus T2 to the power 4 upon an equivalent emissivity, which is given by 1 over 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1, where epsilon 1 is the emissivity of the first surface, epsilon 2 is the emissivity of the second surface. If you substitute the value, considering area to be 1 meter square, the heat transfer without radiation shield per unit area will be 15.8 kilowatt per meter square, or 15.8 into 10 to the power 3 watt per meter square. In second case, the heat transfer with radiation. Now, in this case, you don't know the value of temperature at this point, which is T3, which is the temperature of the radiation shield. Now, the equation or the expression for the heat exchange between plate 1 and the radiation shield is given by Q1 to 3 as sigma A into T1 to the power 4 minus T3 to the power 4 upon 1 upon epsilon 1 plus 1 upon epsilon 3 minus 1, where epsilon 1 is the emissivity of the first surface, epsilon 3 is the emissivity of the radiation shield. Again, T3 is the temperature of the radiation shield. In a similar way, the heat transfer between the radiation shield and the plate 2 is given by Q 3 to 2 as sigma a T3 to the power 4 minus T2 to the power 4 upon 1 upon epsilon 3 plus 1 upon epsilon 2 minus 1, where epsilon 3 is the emissivity of the radiating shield and this is emissivity of the second surface. Now, by considering the energy balance, we can equate the heat transfer from 1 to 3 to heat transfer from 3 to. If you take the expression for the same, we'll have sigma A into T1 to the power 4 minus T3 to the power 4 upon 1 upon epsilon 1 plus 1 upon epsilon 3 minus 1 is equals to sigma A T3 to the power 4 minus T2 to the power 4 upon 1 upon epsilon 3 plus 1 upon epsilon 2 minus 1. Now epsilon A on both sides will get cancelled. In this case, T1 is known, T2 is known, epsilon 1, epsilon 3 and epsilon 2 values are known to us. The only unknown is T3. If you collect the similar terms on either side and if you get the value of T3, you will have the temperature of the shield as 913.8 Kelvin. Make sure all the temperatures are substituted in Kelvin only. Now the heat transfer with radiation shield will be sigma A T1 to the power 4 minus T3 to the power 4 upon this value. You can use either Q13 or Q23. It brings no difference in the value. Now if you calculate the heat transfer with shield per unit area, it is 1594.6 watt per meter square. Now you have heat transfer per unit area without considering the radiation shield, and you have heat transfer per unit area with considering the radiating shield. Now the second bit of the question is you need to calculate the percentage of reduction in the heat transfer due to the radiation shield. Now that is given by heat transfer without shield minus heat transfer with shield upon heat transfer without shield. Now if you place the values that you have obtained, you will get 89.9% of reduction after introduction of radiation shield. Now these kind of problems are very important from the point of your examination. Let us move to the next problem. This problem is on V factor or shape factor, which gives what fraction of energy has been transferred from one phase to another phase. You can have different cases. The phases could be opposite to each other. The phases could be perpendicular to each other. In this case, the phases are at right angles to each other. Two rectangular surfaces are perpendicular to each other with a common edge of 2 meters. The horizontal plane is 2 meters long and vertical plane is 3 meters long. Vertical plane is at 1200 Kelvin and has an emissivity of 0.4. The horizontal plane is at 18 degrees Celsius and has emissivity of 0.3. Determine the net heat exchange between the plates. Now, in order to answer this, you have an equation. He has asked you to calculate the heat transfer from 1 to 2. We will again use the Stefan-Boltzmann equation. Now, this formula is given in your data handbook. I'm referring to 8th edition of Heat and Mass Transfer Data Handbook. It is in page number 84. Even for 6th edition, the page number remains the same. Now, if you take the area of the horizontal plane, comes out to be 4 meters square, and the area of the vertical plane is 6 meters square. Now, if you take the help of data handbook, then you have the same situation of perpendicular rectangles in page number 95. In this case, you have two values. One is x by z, and the one is y by z. One is z by x, sorry, and the one is y by x. So x being the common edge that has been shared by both the surfaces. If you take the value of z by x, it is 1.5, and y by x, it is 1. Referring to page number 95, if you take the value of shade factor 1 to 2, you will get the value of F1 on 2 as 0.22. In this case, you don't have a direct value, you need to take the interpolation. by taking the interpolation value, you will have the shape factor as 0.22. And once you know this value, you can substitute in the equation of Q12. Here A1 has to be considered. So the value of A1 is 4 meters square into 5.67 into 10 to the power minus 8. In this case itself, you can consider the direct values. And this is in degree Celsius. Please note here, convert that to Kelvin scale. And if you substitute the value of emissivities as 0.4 and 0.3 for first and second surface respectively, you will have the heat transfer from surface 1 to 2 as 61,657.7 watts. With this, I will stop here. Next class, we will discuss some more problems related to shape factor. Thank you.